Hello everyone, today we're going to be going through the A-level physics topic of gravitational fields. So let's get started by first defining what exactly we mean by a gravitational field. You already know that gravity is an attractive force between any two bodies which have a mass, and the more massive an object is, the greater its gravitational pull. Now, what do we mean by a field in physics? A field is defined as an area in which a force interacts. So when we talk about a gravitational field, what we're saying is a zone in which the force of gravity exerted by an object acts and interacts with other objects. So a quick recap from GCSE. You'll have already learned that Newton's second law can be used as a way to describe mathematically the effects of a force, which is given by the equation: the force on an object is equivalent to the object's mass multiplied by its acceleration. You'll also remember that the force of gravity acting on an object due to the gravitational pull of the Earth is known as the object's weight, which can be given via Newton's second law equation. The weight of an object is equivalent to the object's mass multiplied by the acceleration due to gravity, denoted as small g, which on Earth is always equal to 9.81 meters per second squared. So when we're modeling gravity in this way, we're making a huge assumption about the nature of the gravitational field on Earth. And that is that the field is uniform. What do I mean by the gravitational field is uniform? It means that no matter where you are, if you're within the field, the force acting on you on an object is exactly the same. No matter if you're an aeroplane way up in the sky or this little guy on the surface of the planet, the gravitational force, that is the g in our equation, remains the same, 9.81 meters per second squared. So what we find is for small distances above the surface of the Earth, this equation will hold true. But when we extend a little bit past that, say in the example of a satellite which is orbiting way above the planet's surface, if we try and model its motion, if we try and model its gravitational pull towards the Earth using the equation that we've written down here, it actually doesn't quite work out like that. And this causes problems for us, as you'll probably guess. We need to be able to model the forces on orbiting satellites and figure out, say, how Earth is affected by this gravitational pull by the Sun and other planets, and we can't do that using the equations that we already have. So, what's the solution to this issue? It was discovered by Sir Isaac Newton, who figured that our assumption for the nature of the gravitational field is actually wrong. It's not a uniform field, but a radial field. And what does this mean? It means that the force exerted on objects within the field changes based off the object's position. So if I were on the very surface of the Earth, the gravitational pull that I would feel is actually much stronger than the pull of a satellite which is way out into the upper atmosphere and beyond. When we're talking about gravitational fields, we always assume that the source of the gravitational force is the center of the Earth in all of the mathematics and in all of the equations, and everything is being pulled towards this central point. Now, Newton also found a way to describe his theory mathematically using this equation. That is, the force due to gravity is equal to a constant, denoted as big G, multiplied by mass 1, multiplied by mass 2, divided by the radius, or distance, squared. So let's break down this equation very quickly for you. G in the equation is known as the gravitational constant. Which is equivalent to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. An ugly unit, I know. You won't have to remember this number for the exams because it'll be given in the A-level physics formula booklet. Now, if we're taking the case of this satellite orbiting around the Earth, we'll label the satellite's mass as m1, for example, the Earth's mass as m2, and the r in the equation is the distance between the source of our gravitational field and the object that's interacting with it. And to find out the force that's interacting between this satellite and the Earth, we would just have to plug in our values of the mass of the satellite, mass of the Earth, and radius between them to determine this value.